Hello, and welcome to Cyber Risk Management in Practice. In this final chapter, we shift our focus to some of the emerging technologies and challenges shaping the future of cyber risk, starting with generative AI. Now, there's a lot of hype around generative AI, but let's be clear, this isn't just another buzzword. It's a real shift in how machines interact with human knowledge and creativity. And it brings both opportunities and risks that cyber risk professionals need to understand deeply. So let's start with the basics. Generative AI systems are trained on vast amounts of data to identify and reproduce patterns. In the case of language models like ChatGPT, they're trained to predict the most likely next word or token based on all the previous ones. That word token is important. These models don't think in words the way we do. They break text down into chunks called tokens, which might be whole words, parts of words, or even punctuation. When a user inputs a prompt, the model doesn't go searching for the right answer in a database. Instead, it generates a response, token by token, predicting what's likely to come next based on everything it has learned from its training data. This approach is powerful, but it also means the outputs can be surprisingly fluid and occasionally wrong. The model doesn't know whether the answer is true or accurate. It knows whether the next token fits a pattern based on probabilities. And that opens up a whole set of risks. One of the most significant is hallucination, when the model confidently presents information that's completely made up. This can be especially dangerous if the output is used in critical decision making or shared publicly without proper review. There's also the issue of data contamination. If users submit sensitive or proprietary information into a public AI system, the data might be retained or even influence future outputs. Then we have bias. These models are only as good or as flawed as the data they're trained on. If the training set includes biased, harmful, or skewed content, the model can reproduce or even amplify those patterns. And from a security perspective, generative AI can lower the barrier for attackers. It can be used to generate realistic phishing messages, malicious code snippets, or social engineering scripts that are harder to detect and easier to scale. So while the business potential is huge, the risk surface expands dramatically. We've talked about how generative AI models work and the risks they introduce, but how are organizations actually using them? The short answer is everywhere. In marketing, generative AI can write campaigns, social posts, and even tailor content to individual customer profiles. In software development, it helps write code, explain bugs, and translate between languages. Legal, HR, finance, data science, all of these functions are starting to incorporate generative tools into their workflows. And that's why we can't afford to treat this like a theoretical issue. The tools are being adopted, often by individuals and teams without formal oversight, which means we need a governance model that keeps up with the pace of experimentation without getting in the way. That's where structured frameworks come in. Let's start with the NIST AI Risk Management Framework. This framework isn't just for engineers. It's designed to help organizations manage AI risks across different domains with a balance of technical and non-technical controls. It's built around four key functions: govern, map, measure, and manage. Govern is about defining policies, roles, and accountability. It asks, who owns the AI initiative? Who monitors the risks? What guardrails are in place? Map means understanding the context of the AI application, how it works, what it's meant to do, and where things could go wrong. Measure focuses on evaluating performance, bias, robustness, and potential harm. It's about checking whether the AI is doing what it's supposed to and flagging when it's not. And manage is where action happens. It's the ongoing process of adapting, improving, and responding as the environment shifts and new risks emerge. These four functions help structure conversations between technical teams, business leaders, compliance officers, and risk managers. If you need something more formal, especially in international contexts, you might also look at ISO 42001. This new standard is all about building an artificial intelligence management system, a governance structure that ensures AI is used responsibly, ethically, and transparently. It covers things like lifecycle management, risk treatment, traceability, documentation, and accountability for decisions. It doesn't tell you what to build, it tells you how to think about what you're building and how to document and control it. That matters because the risks with AI aren't just about bias or hallucinations. They're about trust. Can you explain how a decision was made? Can you audit the training data? Can you trace where a recommendation came from? These questions aren't just academic. They're starting to show up in regulations, procurement processes, and public expectations. And they become even more important when your AI is third-party provided. Many generative tools come from external vendors or are embedded in broader platforms. That means you need to assess them like you would any other supplier, looking at privacy, security, control, and contractual protections. You can't just trust the brand. You have to ask the same questions you'd ask of any critical system, because at the end of the day, you're still responsible for the outcomes. Now, we'll shift gears and explore another game-changing technology, quantum computing, and why it's already starting to change how we think about encryption, risk timelines, and long-term resilience. Quantum computing has been a topic of fascination for decades, but it's no longer just a research subject. It's advancing fast, and it's bringing new urgency to how we think about cybersecurity. The technology itself is radically different from what we use today. Traditional computers process information in bits, ones, and zeros. Every operation is based on flipping those binary switches. Quantum computers use qubits, which can represent both 1 and 0 at the same time through a principle called superposition. And they can also be entangled, meaning the state of one qubit is linked to the state of another, even across distance. Together, these principles allow quantum computers to process certain types of problems exponentially faster than classical machines, and that creates a massive risk for the cryptographic systems we use today. Much of our digital security, whether it's data in transit, secure communications, authentication, or digital signatures, relies on algorithms that are hard to break using traditional methods. For example, RSA encryption is based on the difficulty of factoring large prime numbers. Elliptic curve cryptography relies on the complexity of the discrete logarithm problem. But with quantum computing, those problems aren't so hard anymore. An algorithm called Shor's algorithm can theoretically break RSA and ECC using a powerful enough quantum computer. And that's not just a future concern. It's a problem today because of something known as harvest now, decrypt later. That means attackers could be collecting encrypted data today, knowing they'll be able to decrypt it once quantum computers become strong enough. Think about sensitive data with a long shelf life, trade secrets, medical records, government communications, proprietary research. Even if it's secure today, it may not be secure in 10 years. That's why organizations need to start thinking about quantum readiness now, not when it becomes urgent. And readiness starts with awareness. So let's walk through what quantum resilience looks like in practice, how to assess your exposure, understand the emerging standards for post-quantum cryptography, and begin building a plan for transition. So let's start by defining what does it mean to become quantum resilient. It starts with understanding where and how your organization currently uses cryptography. That might sound straightforward, but in many cases, it's not. Encryption is embedded everywhere in browsers, APIs, cloud services, hardware modules, mobile apps, internal tools. Some of it is managed directly, some of it is handled by vendors, and some of it is buried in legacy systems that no one's looked at in years. A critical first step is to create a cryptographic inventory. What encryption algorithms are in use? Where are they implemented? Which ones are exposed to external communications? Which systems rely on them for authentication, secure storage, or compliance? Once you have that visibility, you can start identifying the systems most at risk if current encryption methods become obsolete. This is where post-quantum cryptography comes in. Post-quantum algorithms are designed to be secure against both classical and quantum attacks, and they're already being standardized. After years of evaluation, NIST has selected a set of algorithms as the basis for future cryptographic standards. Kyber for key encapsulation, dilithium for digital signatures, Sphinx Plus as a stateless hash-based alternative. These algorithms don't just resist quantum attacks. They've also been tested for performance, robustness, and suitability in real-world applications. Transitioning to post-quantum crypto won't be a single upgrade. It will be a multi-year process, and it needs to be planned accordingly. That means looking at product development timelines, vendor roadmaps, regulatory guidance, contractual obligations, and compatibility with existing infrastructure. It also means building flexibility into your crypto agility so that future transitions can be done with less friction. There's a broader mindset shift here, too. Quantum risk isn't just a technical issue, it's a business risk that we can see now in the horizon, and we must act now to be ready when it materializes. This is a great reminder that our assumptions about security lifespans need to evolve. The risks we model today can't just be based on what's feasible this year. They have to account for future capability, data longevity, and the pace of change. That's why this book ends not with a checklist, but with a mindset. In the book, we return to the idea of the vortex. Cyber risk management isn't a straight line. It's a loop that gets tighter and more responsive over time. And the more adaptive your program becomes, the better prepared you'll be, not just for quantum or AI, but for whatever comes next. If this approach resonates with you, there's a lot more discussed in the book. Find your copy and embark on this journey with me, improving your cyber risk management program step by step with a practical approach.